Today we're going to learn lesson 10, rational equations and inequalities with applications. The expectations are, after this lesson, you should be able to solve rational equations algebraically and solve rational inequalities algebraically and solve real-world problems involving rational equations or inequalities. So first, let's have a look at how do we solve rational equations algebraically. So usually there are two methods. First method can be summarized in this way. First, we convert the equation into a form like this, and the ratio between px and qx is 0. This is actually equivalent to the numerator is 0 and denominator is not 0, right? And using this way, we can convert the rational equations into probably two polynomial equations. And then we can use the method to solve polynomial equations to solve this question, right? And there's another method. As long as you control the x variable in the domain, a form of an expression with this form can be equivalent to AD equals BC by using the cross multiplication, right? So note, in either way, you need to ensure that you always use equivalent transformations. Domain should never be changed, okay? All right, so let's have a look at some examples to illustrate these measures. Okay, let's see this example first. Solve the equation 4 over 3x minus 5 equals 4. Okay, I'll give you 3 minutes to think about that first. Right, have you finished? So as we mentioned, there are two methods, right? So let's have a look at method 1. The original equation is 4 over 3x minus 5 equals 4, right? So this is equivalent to, first of all, we can divide both sides using a 4. This is equivalent to the original expression, right? And next, we can move the 1 in left side. And then it becomes minus 1, right? And then rewrite the whole expression in left side using the common denominator, which is 3x minus 5. Okay, so the original problem is converted to minus 3x plus 6 over 3x minus 5 equals 0, right? And this is equivalent to the numerator must be 0 and denominator cannot be 0, right? Which is further equivalent to x equals 2 and x cannot be 5 over 3, right? If we consider this, this can be further simplified to x equals 2. So x equals 2 is the solution of the original equation, right? Okay, so let's have a look at the second method. For the second method, original expression is this. This is equivalent to, again, first of all, let's simplify this equation to this one by dividing both sides using a 4, right? And this is equivalent to, first we need to control that the denominator cannot be 0, right? And as long as you ensure the denominator is not 0, then we can use cross product, right? So 3x minus 5 is 1. This is equivalent to x cannot be 5 over 3. And 3x is 6, which is actually x equals 2, right? And if we consider both of these, the final solution is x equals 2. Do you understand? You can choose either method you feel comfortable with. All right, you can also check the two methods here after class. All right, so let's have a look at another example here. Again, I'll give you 3 minutes to think about this. All right, so let's have a look at how we can solve this question. So for this type of question, apparently that method, second type of method seems much easier, right? Okay, so the original equation is equivalent to, okay, first of all, let's factor the denominator first. This can be factored to x plus 1 times x minus 4, right? Equals 3x plus 2. Again, this can be factored to x plus 1 and x minus 1, right? Okay, now we can see that there is x plus 1 here and x plus 1 here, but do not hurry to cancel two terms here, because if you just directly cancel them, actually you will probably lose, you probably change the domain. So first of all, you need to ensure that you control the domain first. First of all, x cannot be minus 1, x cannot be 4, right? And x cannot be 1. Okay, as long as you control the domain, then we can use cross multiplication, and then we can cancel these two. So the original equation is equivalent to, by cross product, we have x minus 5, x minus 1 equals 3x plus 2 times x minus 4. Okay, do not forget this. This is very important. Okay, this is equivalent to x cannot be minus 1, x cannot be 4, x cannot be 1. And then let's expand everything and try to simplify. 3x squared minus 10x minus 8. X squared minus 6x plus 5 equals 3x squared minus 10x minus 8. And this is equivalent to x cannot be these values. And then we can simplify the second part to 2x squared minus 4x minus 13 equals 0. So let's call this asterisk. So this is actually a quadratic function, a quadratic equation, right? We can use the formula to find its two roots. So first of all, the determinant is 16 positive or negative. Determinant is 16 minus 4 times 2 times minus 13, right? Which is 16 plus 104, which is 120, right? Which is greater than 0. So the two roots for the asterisk are x equals 4 here, 4 here, positive or negative, square root of 120, which are 2 negative or positive 30 over 2, right? Okay, so that means these two roots might be the two roots of the original equation, but we need to check if the roots we have found violates the domain here. So none of the two roots are minus 1, 4, and 1, right? So the roots here can be kept. Okay, the conclusion is x is 2 positive or negative square root of 30 over 2. This is our final solution. Okay. All right, any questions? Okay, you can also check the solution here after the class, okay? All right, here we do another practice. I'll give you 3 minutes to think about this. All right, so let's have a look at how we can solve this problem. All right, apparently we can use second method, right? Original equation equivalent to, first of all, we need to control that the denominator here cannot be 0, right? As long as we have controlled the domain, the original equation is equivalent to x plus 1 equals -1 times x squared minus 2x minus 3, right? Okay, and next, first of all, control the domain. X squared minus 2x minus 3 is x minus 3 times x plus 1. This cannot be 0, right? Next, let's expand and simplify. So x plus 1 equals minus x squared plus 2x plus 3, right? Okay, so next, this is equivalent to x cannot be 3 and x cannot be -1. Next one, x squared minus x squared minus x minus 2, right? Equals 0. And this is equivalent to x cannot be 3, x cannot be -1. And then let's factor this expression here to x minus 3, x plus 1. This is 0, right? And this is equivalent to x cannot be 3, x cannot be -1. And the roots of the second equation is x equals 2. or x equals -1, right? And if we consider all of the conditions here, this is probably a possible solution, right? And this is another possible solution. But here, you should pay attention that x cannot be 3 and x cannot be -1. So the solution here cannot be accepted because it will make the denominator be 0. Okay, so consider all of these. The final solution is x equals 2. Okay, this is our final solution. Okay, do you have any questions? No? All right. You can also check the solution here. Sorry, there is a typo. This should be a coefficient 1, not 2. All right, any questions? Okay, let's have a look at how do we solve rational inequalities algebraically. So typically there are 4 types of inequalities. First one, you might have a ratio between 2 polynomial functions, and the ratio is greater than 0. If you have a type like this, this is equivalent to the sign in front of px and qx should be the same, right? So that means they can either both be positive or both negative. Understand? And similarly, for the second type, if you have px over qx less than 0, this means the signs in front of the 2 expressions must be different, right? So that means either you have px greater than 0, qx less than 0, or you have px less than 0 and qx greater than 0. Understand? Okay, the third type is if px over qx is greater than or equal to 0. This is actually equivalent to the later 2 parts. First part is px over qx can be 0, or px over qx can also be greater than 0. And then we can solve the later part using the same method illustrated here, right? Which means the signs in front of the 2 expressions must be the same. Okay, in order to solve the equation here, note that the qx cannot be 0. Do not forget this, right? Qx cannot be 0 and px must be 0. Okay, the fourth type is similar to the third type, in which you have px over qx less than or equal to 0. So this is equivalent to a equation and an inequality. For the equation, in order to solve it, you need to ensure that px is 0 and qx is not 0. And for this inequality, if px over qx is less than 0, this means the signs in front of px and qx are different, right? So you can either have px is greater than 0, and at the same time qx is less than 0, or you can have px is less than 0, and at the same time qx is greater than 0, right? Okay, so pay special attention. Always use equivalent transformation. You could never enlarge or reduce the domain, okay? For example, usually you cannot do this. A over b greater than c over d. Do not just use the multiplication without considering the signs in front of the b and d, right? Because if you cannot determine the signs of b or d, you don't know if you need to change the direction of the inequality symbol here. Understand? Okay, so let's have a look at an example. Solve the following inequality: 2 over x minus 5 less than 0. Okay, I'll give you 2 minutes to think about this. All right, have we finished? Okay, let's have a look at how do we solve this. A rational inequality is equivalent. First of all, we can put the 0 to the left-hand side. And this is equivalent to, we can rewrite the whole expression on the left-hand side using the common denominator, which is x minus 5, right? And this is equivalent to minus 10x plus 52 over x minus 5 less than 0, right? And as you can see here, a ratio that is less than 0, this is equivalent to the numerator and denominator must have different signs in front of them, right? So you can either have minus 10x plus 52 less than 0, and at the same time, x minus 5 greater than 0. Or the numerator here is greater than 0 and denominator at the same time is less than 0, right? And this is equivalent to x greater than 5.2 and x more than 5, or x less than 5.2 and at the same time x less than 5, right? Okay, now we can use a number axis to determine the final solution. So for the first branch, this is 5, this is 5.2, right? So first of all, x should be greater than 5.2 here, and then x should be greater than 5. So the final solution of the first branch is overlapped area here. This means first branch equals x greater than 5.2. Okay, let's consider the other branch, 5.2 here. Second branch states that x should be less than 5.2. And then x should also be less than 5, right? So the overlapped area is here, which means x should less than 5. All right, so if we consider both of the two branches, x could either be greater than 5.2 or x can also be less than 5. So the final solution is x greater than 5.2 or x is less than 5. This is our final solution. Okay. Or if you use the interval notation, you can also write it like this. X belongs to the union of the two intervals. First is negative infinity to 5. Second is 5.2 to positive infinity. Okay, you can also write it in an interval notation. Both of these notations here are correct. Okay, you can also check the solution here. This is a nice writing of the solution. You can also check it after the class, all right? Okay, let's see another example. This time the inequality is more complex. Okay, I'll give you 3 minutes to think about this. All right, let's have a look at how we can solve this. Okay, original inequality is equivalent to, all right, first of all, this is equivalent to an equation and an inequality, right? So we can either have the ratio be 0, right? Or the ratio here is greater than 0, right? Which is equivalent to, okay, next let's factor the expression in the numerator and denominator. So this is why we have practiced a lot on factoring, right? Or we can also have x minus 2 times x plus 1 over x plus 4, x minus 3 greater than 0, right? Okay, next, for this equation, if you have a ratio that is 0, this is equivalent to the numerator is 0, but the denominator is not 0. And for the inequality here, the ratio between two expressions is greater than 0. This means the signs in front of the two expressions are the same, right? So we could either have a positive numerator and at the same time a positive denominator, or we can also have a negative numerator and a negative denominator, right? Okay, next, for this equation, x minus 2 times x plus 1 equals 0. This is equivalent to x equals 2 or x equals minus 1, right? And for the second part, x cannot be minus 4 and x cannot be 3, right? Or, okay, let's solve the first inequality. So first of all, let's solve this. This is actually a quadratic function on the left-hand side, right? So let's try to sketch its graph. X minus 2, x plus 1. There are two zeros, right? One of them is minus 1. The other one is 2. And the leading coefficient is positive. So this function opens up. And the interval that makes this function above 0 is here and here, right? So the solution for the first branch is x either less than minus 1 or x greater than 2, right? Okay, now let's consider the second one. Second one, also we consider the quadratic function on the left-hand side. There are two zeros. One of them is minus 4. The other one is 3. And the leading coefficient is 1, which is greater than 0. So it opens up. So it has a sketch like this, right? In order to have it greater than 0, x should be less than minus 4 or greater than 3, right? The solutions are x less than minus 4 or x is greater than 3, right? Or for the same function, this time we check which interval can make it less than 0. So for less than 0, this is a interval here in the middle, right? So for the second branch, x should be greater than minus 1 and less than 2. And again, same function with this one. And this time we need to check the interval that makes this function less than 0, which is here. X greater than minus 4, less than 3, right? Okay, then we need to try simplify each of the solutions. First of all, x can be 2 or x can also be minus 1, right? If x is 2 or x is minus 1, of course, x is not minus 4, x is not 3 either. So we can just cancel this, right? So next one, we can analyze the solution using a number axis. So there are 4 numbers, right? -4, -1, 2, 3, right? Okay, first of all, x is less than -1. So less than -1 here. And x is greater than 2. Greater than 2 is here, right? And then x is less than -4. So less than -4 is here, and greater than 3. Greater than 3 is here. Now let's consider the overlapped area. Because x must satisfy both of the conditions, right? So we need to find the overlapped area. So we can find one on the left-hand side and the other one on the right-hand side. So the final solution for this branch is x is either less than -4 or x is greater than 3. This is a solution of the second branch, right? Or we can have the third solution. Okay, again, we check the final solution for this branch using a number axis. -4, -1, 2, 3. These are the 4 numbers here, right? So first of all, x is greater than -1 and less than 2. And then x is greater than -4 and less than 3. Okay, so x should satisfy both the conditions. So the overlapped area is here. So the solution of the third branch is x greater than -1 and less than 2. Okay. All right, so these are the possible solutions of this question. And actually, we can combine x equals 2 with this one, and x equals -1 with this one, right? So the final solution is x is -4, x less than -4, or x greater than 3, or x can greater than or equal to -1 and less than or equal to 2. This is our final solution. Okay, any questions? No? Okay, you can also check the whole solution on the slides after class, okay? Remember, you can also use the interval notation like this. All right, so let's have a look at another example. Solve 4 over x minus 5 less than 3 over x plus 4. Okay, I'll give you 2 minutes to think about this. All right, let's have a look at the solution here. All right, so we can move everything on the left-hand side first, right? So the original inequality is equivalent to 4 over x minus 5 minus 3x plus 4 less than 0, right? Okay, now let's rewrite the expression here using the common denominator, which is x minus 5, x plus 4. Then this is 4x plus 16 minus 3x plus 15, right? Which is less than 0. And simplify this, we can get x plus 31, x minus 5, x plus 4 less than 0, right? Okay, now we have a ratio that is less than 0. This means we can either have the numerator is less than 0, and at the same time, the denominator must have different sign, which is greater than 0, right? Or you can also have the numerator is greater than 0, and at the same time, the denominator is less than 0, right? Okay, so for the first branch, first of all, x plus 33 less than 0, this is equivalent to x is less than minus 31. And then we need to consider this is a quadratic function, right? It has 2 roots and it's opening up. First root is x being minus 4, next one is x equals 5. So the intervals that makes this function greater than 0 is here and here, right? So this is equivalent to x is less than minus 4, or x is greater than 5, right? Or for the second branch, first of all, x must greater than minus 31. Next one, the same function with the previous quadratic function, but this time we need to find the interval that makes this function less than 0, which is x greater than minus 4, less than 5, right? Okay, so this is equivalent to first branch. All right, so this time, again, you can use a number axis to decide the solution of the first branch. So there are 3 numbers. First one is minus 31. Next one is minus 4. Next one is 5. Okay, it's not necessarily to scale. As long as you keep the relative positions correct, you'll be fine. So first of all, x is less than 31, right? Next one, x is less than minus 4. So less than minus 4 is here, and then x is greater than 5, right? So the overlapped area apparently is here. So the solution of the first branch is x less than minus 31. Okay, now let's consider the second branch here. Again, we have 3 numbers, minus 31, minus 4, and 5. First of all, x should be greater than minus 31. And then next, x is greater than 4 and less than 5. The overlapped area is here, right? Okay, so the solution of the second branch is x is greater than minus 4, less than 5, right? Okay, so the final solutions is x is either less than 33 or x is greater than 4 and less than 5. This is our final solution. Okay, any questions? Okay, you can also check a nice writing of the solution on these slides after the class. All right, so if you do not have any questions, this time it's your turn to solve this question. Okay, I'll give you 3 minutes to think about this. All right, any thoughts? So we have a ratio that is less than or equal to 0, right? So this is equivalent to, first of all, the ratio can be 0, right? Or the ratio here can also be less than 0, right? It is equivalent to an equation and an inequality. And for the equation here, if we have a ratio that is 0, that means numerator is 0 and denominator is not 0, right? And for this inequality, if you have a ratio that is less than 0, that means the signs in front of the two expressions are different, right? So first of all, we can have the numerator less than 0 and the denominator is greater than 0, or the numerator is greater than 0 and at the same time the denominator is less than 0, right? And this is equivalent. In order to solve them, it's better to factor each expression, right? For the first one, it is factored to x minus 4 and x plus 1 equals 0. For the next one, it can be factored to x plus 5 and x plus 6 cannot be 0, right? Okay, so similar thing here. Or, okay, similar expression, just copy them here. And okay, next, let's try to solve them. For the equation here, x can be 4, right? Or x can be minus 1. And x is not minus 5. And x is not minus 6. Or for the second branch, first of all, let's consider the function here. This is a quadratic function that is opening up. There are two roots. One of them is minus 1 and the other one is 4, right? The interval that makes this function less than 0 is here, right? So the solution is x greater than minus 1, less than 4. For the second one, it's opening up. 4 roots are minus 6, minus 5, right? Greater than 0 means here or here, right? So x is less than 6 or x is greater than minus 5. Okay, next branch. Okay, same function here. And this time we need to find the intervals that makes this function greater than 0. So x less than minus 1 or x greater than 4, right? Okay, for the function here, we consider this graph. As you can see here, when x is greater than 6 and less than minus 5, this function is less than 0, right? Okay, so we have all the solutions here. Let's try to simplify them. Okay, first one, x is 4 or x is minus 1. Of course, when x is 4 or x is minus 1, x cannot be minus 5 or cannot be minus 6. So we can just cancel this, right? Okay, next branch, we can consider this using a number axis. So there are 4 numbers, minus 6, minus 5, minus 1, and 4, right? First of all, x is within minus 1 and 4, which is here, right? Next one is x less than minus 6 and or x is greater than minus 5, right? The overlapped area is here. So x greater than minus 1 and less than 4. This is the second solution. And next one, also we use a number axis, minus 6, minus 5, minus 1, and 4. All right, this time, first of all, x is less than minus 1 and greater than 4, right? And next, x is within minus 6 to minus 4, minus 6 to minus 5. So the overlapped area should be here, right? So the solution is x greater than minus 6, less than minus 5. Okay, if we consider all of these solutions, the final solution is x is either greater than -1, greater than or equal to -1, or and less than or equal to 4, right? This is one of the possible solutions. Or the other solution is x is greater than -6 and less than -5, right? Okay, please have a look at this. You can also check the solution on this slides here. Okay, any questions? No? Okay, so let's have a look at the next key point today. Solve real-world problems involving rational equations or inequalities. So this is actually similar to what we have learned so far, except that there is additional step here, right? First of all, we need to model the problem stated in natural language into mathematical expressions. Pay special attention to the domain, because for real-world problems, domain is actually much it's actually limited to a smaller interval, right? This must be determined according to the real world cases. Okay, after that, we can solve the mathematical model and make conclusion. All right, let's see an example here. The intensity of sound in watts per square meter varies inversely as the square of the distance in meters from the source of the sound. The intensity of the sound from a loudspeaker at a distance of 2 meters is 0.001 watts per square meter. A, determine a function to represent this relationship. B, graph this function. C, what is the effect of halving the distance from the source of the sound? Okay, I'll give you 2 minutes to think about it, and then let's have a look at the solutions together. All right, any thoughts? Okay, let's have a look at the solutions together. First, we can let I represent the intensity of the sound, right? And then let D represent the distance from the source of the sound. I varies inversely as the square of D. So we can express I equals K over D squared, right? Because they have I varies inversely as the square of D, where K is a constant, right? And then we know that when D is 2, I is 0.001, right? So if we put this point here in that equation, we can find the value of K, right? Okay, so that means 0.001 equals K over 2 to square. Then K is solved to be 0.004, right? Okay, so the relationship we're looking for is I equals 0.004 over d squared. Of course, you need to pay attention to the domain here. D is the distance from the source, right? So d is greater than 0. And because d here is in the denominator position, d cannot be 0. So pay attention to the domain here. Okay, so the graph of this function, this is actually, you can consider the reciprocal of a quadratic function, right? All right, and then stretch this function by a factor of 0.004, right? So this function will have a shape like this. The vertical asymptote is actually the x, the y-axis, which is x equals 0, right? Okay, because d is greater than 0, so there's no need to grab the other branch, right? Okay. C. What is the effect of halving the distance from the source of the sound? Okay, so if we consider the equation here, when d becomes 1 over 2d, that means I is 0.004 over d squared over 4, right? Which is 4 times 0.004 over d squared, which is 4 times I, right? So that means if you have the distance, the intensity is stretched by a factor, is enlarged by a factor of 4, right? So if the distance is halved, the sound is 4 times as intense. Okay, any questions? No? Okay, let's see. Let's do a practice. The maximum time t in minutes a scuba diver can rise without stopping for decompression on the way up to the surface is defined by the equation Td equals 525 over d minus 10. And of course, the domain is d is greater than 10, where d is the depth of the dive in meters. For the maximum time to be less than 30 minutes, how deep can a diver dive? Okay, I'll give you 2 minutes to think about this question. All right, let's have a look at the solutions together. So this time, because we want the maximum time to be less than 30 minutes, right? So we can just let TD, the expression here, less than 30, right? Also note that D is greater than 10, and then solve for distance D. So this inequality here is equivalent to 5 to this one, right? So we need to consider the expression, the inequality, and the domain together. So this is equivalent to, if we control d is greater than 10, that means d minus 10 must be a positive number, right? So if it is a positive number, we can multiply both sides of the inequality here using a positive number, then the direction of the inequality symbol does not change, right? So now we can use the equivalent sign here. This is equivalent to, first of all, d is greater than 10. Next, 525 is less than 30d minus 300, right? And then it's equivalent to d is greater than 10 and 30d more than 825, right? Okay, if we simplify this, d is greater than 10 and d is greater than 27.5. So 10 is here, 27.5 is here, d is greater than 10 and d is greater than 27.5. The overlapped area must be here, right? Which is d should be greater than 27.5. And then now we can make these conclusion. The diver should dive more than 27.5 meters so that the maximum time can be less than 30 minutes, right? Okay, any questions? Okay, now let's have a look at another example. Sketch the function gx is a ratio between two quadratic functions. Okay, I'll give you 1 minute to think about this. All right, any thoughts? Okay, first of all, it's better to simplify this function, right? So if we factor the numerator, it is actually x minus 4 times 2x plus 1, right? And for the denominator, it's actually x plus 2 times 2x plus 1, right? Actually, we can cancel these two, right? But before you do that, pay attention to the domain. Okay, the domain is x cannot be minus 2. X cannot be minus 1 over 2. You need to control the domain first. After that, then you can cancel these two terms here, two factors here. Otherwise, you might lose some parts of the domain, right? Okay, so basically gx is x minus 4 over x plus 2, and x cannot be minus 2 and x cannot be minus 1 over 2, right? And then we can try to sketch this function and remove the 2 points here. This is a graph of the gx, right? Okay, we have already learned how to graph the ratio between two linear functions. First of all, x cannot be minus 2. That means x minus 2 might be a asymptote, right? Okay, so this is a vertical asymptote, which is x equals minus 2. And when x approaches infinity, the gx approaches the ratio between the two coefficients here, which is 1, right? Okay, so gx equals 1 is the horizontal asymptote. And when x is 0, we know that gx is minus 2, right? Okay, so 0, 2 is here. Okay, so this function is having a shape like this. The other branch is like this, right? But remember to remove these 2 points here. When x is minus 2, x cannot be minus 2. Of course, we have controlled this. And the other one is x cannot be minus 1 over 2. So minus 1 over 2 is here, right? So when x is minus 1 over 2, gx is minus 1 over 2 minus 4 minus 1 over 2 plus 2, which is minus 3, right? So we need to remove this point here. You need to put a circle here. That means the gx cannot be the point there, which is -1/2 minus 3, right? Okay. You can check the solutions on this slide here. This is a nicer drawing of the graph. Remember to remove the point here, okay? This is very important. Note that there is a hole at the point -1/2 minus 3. Okay, and next let's do a practice. Sketch the function f(x) equals x² minus x minus 6 over x plus 2. Okay, I'll give you 2 minutes to think about this. Okay, let's have a look at the solutions. So first of all, let's simplify this equation. Simplify this function. So fx is x minus 3 times x plus 2 over x plus 2, right? And note that x plus 2 is in the denominator position. So first of all, x cannot be minus 2, right? If we control x cannot be minus 2, then we can cancel the x plus 2 here. So this is equivalent to fx is actually x minus 3, and x is not minus 2, right? And we have already know that x minus 3 is a line like this, right? With a slope of 1 and y-intercept 0 minus 3. And remember to remove the point x being minus 2 here. So you need to remove this point, which is -2 minus 5, right? Because on this line, when x is -2, y is -5. So we need to remove this line here. Okay, so a formal sketch of the graph of fx is shown here. You can check the graph after the class, okay? All right, any questions? No? Okay, let's make a summary of today's lesson. So now you should be able to solve rational equations algebraically and solve rational inequalities algebraically as well. Also, you should be able to solve real-world problems involving rational equations or inequalities. Pay special attention to the domain, okay? Pay attention to the domain. Okay, always be careful with this. All right, so if you don't have any questions, today's class is over. I'll see you next time. And remember to download the homework and submit it on time, okay? All right.